First, I want to thank the organizer for organizing this conference and invite me to give a talk. So in this talk, I'm going to talk about thermal quantum state preparations using system bus copying dynamics. And in this talk, I will mainly focus on introducing the results in these two papers, and I will slightly touch upon the third paper here, and these are all my wonderful for collaborators for this work. So basically, in this talk, the problem we want to solve, so at least the problem statement is very simple. I have a Hamiltonian capital H and some inverse temperature beta, and I only assume access to the Hamiltonian simulation. So meaning that I don't need to know the structure of my Hamiltonians. I don't need to know the spectrum or the eigenvectors of my Hamiltonian. And I want to use quantum computer to prepare the thermal state corresponding to the inverse temperature beta. So if I let the temperature go to 0, this basically means beta go to plus infinity, then these problems will be transferred to the ground state preparation problem. Okay, so essentially these two problems are closer to connect with each other. One applications of these two problems is it can help us to prepare the initial state for the phase estimations. And here the key is we only use Hamiltonian simulation, exponential minus ITH. Okay, so now before introducing the algorithms, I want to give some intuitions about this algorithm. Essentially, we will use open quantum system dynamics to prepare the ground state of a given Hamiltonian. And how you understand the open quantum system dynamics, you can imagine that I have a food, and then you can see my food as my system. Then I put the food into the fridge, then which is the environment. Then I give my fridge some temperature. Okay, then my food will interact with this environment, meaning that I will have some total Hamiltonian simulations acting both on the system part and the environment part. Then after I run this total Hamiltonian for certain time capital T, I can trace out this environment part and only focus on the system part. Then so in nature, we always have thermalization phenomenon. The basic meaning is the temperatures of my systems will converge to the temperatures of my environment. This basically means my system density operators will automatically converge to the thermal state with the given temperature. Okay, so if I want to prepare the ground state, what you can do is you can give a very low temperature to your environment. Then in the end, you can expect the density operators for your systems will converge to a state that is very close to your ground state. And this is the very high level ideas of this class of algorithm. Okay, then now we want to build we want to design some algorithms based on this idea. Basically, our questions we want to solve is how to design an algorithm working as a fridge on the quantum computer. We basically want to use quantum computer to simulate this whole thermalization process. Okay. Good. So then in the literature, the first attempt is to use the Lindblad dynamics to simulate the whole process. The idea is very simple. Originally, in the open quantum system framework, we have something called the system bus interactions. Then under the assumption that we have weak interactions between system and the bus, and after some approximation, basically in physics, we require this Bohr, Markov, and circular approximation. We can show that the dynamics of my system part can be approximated by this Lindblad dynamics. Basically, the Lindblad dynamics is a very good mathematical model to approximate the original open quantum system dynamics. Okay. Now, in practice, people can always say that these approximations might not be true, meaning that in a lot of the cases, the linear dynamics is not a good approximation to the system bus interaction framework. However, here I want to emphasize that our goal is to design some algorithm. So even the linear dynamics is not a good approximation to the open quantum system, we don't care about it. We just see it as an algorithm tool with provable guarantees. Okay? This idea was originally proposed by Chifang Chen, Castellano, Brandao, Gillian in 2023, and after they are this fundamental work, in the last 2 years, there are numerous progress towards end-to-end complexity guarantees of this algorithm framework. Basically, in the last 2 years, we have tons of papers in this area, and now what people can do is people can design some linear blood dynamics which guarantees correct fixed point, meaning that your solution can converge to the thermal state or ground state. And we can also guarantee that we can use quantum computer to efficiently simulate this linear blood dynamics. Furthermore, we can also give mixing time guarantees, meaning that I can give you an upper bound about how long I need to run my linear blood dynamics so that my solution can converge to a state which is very close to the ground state. Okay, so here is basically the state of the art for the linear blood dynamics. Now, a natural question to ask is here, since the linear blood dynamics are already very good, what are the new things that we can do? So to answer this
general question, how do you choose those cross operators in general?
Yeah, so very good question. So this will be on these slides. Okay, so here, before I talk about the disadvantage of linear blood dynamics, I first want to quickly show you how it works. Basically, the ideas of linear blood dynamics is I will give a specific design of the coherent part capital G and the jump operator Ka, so that I can ensure the solutions of this linear blood dynamics can converge to the target state. You can imagine that the target state is a thermal state or the ground state. Okay, so in the constructions of these operators, we can ensure that there are some way to find efficient block encodings of this matrix G and the jump operator Ka. So for examples, in most of the literature, this jump operator Ka equals to a linear combination of Heisenberg evolution, where this AA is just some coupling operators you can choose. Okay. Now, in general, after we have this linear blood dynamics, so its simulations involves 2 steps. First, I need to find a way to block encoding this coherent part G and the jump operator Ka. Then after I have this block encoding, I can use the well-developed linear blood simulation algorithms to simulate this dynamics up to time capital T. And this is basically how this class of algorithms works. Okay? So, however, as you can imagine, since the formulas of this jump operators is a little complicated, the block encodings of these jump operators is not very trivial. You often need to use LCU or multi-controlled Hamiltonian simulations or backward Hamiltonian simulation. You also need to use a QFT in some block encoding techniques. So basically, although we can guarantee that on the fault-tolerant quantum computer, we can efficiently simulate this linear blood dynamics, but this algorithm is not friendly to the near future quantum computer. Okay, so then since the linear blood dynamics has this kind of disadvantage, a natural question to ask is, can we find a simpler algorithm that is more suitable for near-term devices where I can still give rigorous guarantees? Okay, And this question is answered by our first paper here. Basically, in these papers, we give a much simpler algorithms than the Lindblad dynamics, and this algorithm can still give us rigorous convergence guarantee. Okay, so the key idea is in our new paper, we will get rid of the Lindblad dynamics. Basically, I will try to engineer my system bus interaction models and see it as an algorithm tool for me to prepare the thermal state and the ground state. So all my design will be on this system bus interaction model level. Okay. Now I will introduce the ideas of this algorithm. So here, so I think this slide is the most important slides in this talk. So first, our algorithms is an iteration algorithm. In each step of my algorithms, I will run the following quantum circuit. And this quantum circuit contains 4 different parts. So first, this quantum circuit contains the forward Hamiltonian simulation. So I want to emphasize that this is only a forward Hamiltonian simulations, not controlled Hamiltonian simulation. Okay? And these algorithms only require a single ancilla qubits, which represents the bus or the environment in the open quantum system. And on this single ancilla bus, I only need to run a single Z rotation here. Okay? And on this quantum, so in this quantum circuit, although I draw a very large rectangle here, but in our implementations, this rectangles is only a 2-qubit gate. Okay, so it's only a 2 local gate, one act on the bus and the one act on the system part. Okay, so essentially, in each step of my algorithms, I will try to run this quantum circuit. Then I will try to do some trace out process to reset my ancilla qubit. And this is a trace out process, meaning that I don't care about the outcome of my measurement, and there is no success probability problem. Okay. Essentially, in each step of my algorithms, I only run this Hamiltonian simulation part plus some trace out. Then this corresponding to a quantum channel phi, and we can design the interactions between the systems and the bus carefully, so that as long as I apply these quantum channels for enough numbers of times, my quantum state can always converge to the thermal state or the ground state. And I don't care about which initial state is.
Usually when I think about a bath, it's way bigger than the system.
Good.
It's 1 qubit here. Maybe the rest of your slides are going to convince me why that will work, or maybe you can just give me some intuition for why 1 qubit is a big enough bath.
Right. So the key here is I do some trace out process. So as another way to view this trace out process is you keep this qubit here, but in each step of my algorithms, I add a new ancilla qubits, which is called repeated interaction framework. Then if you do it in this way, you can imagine that I try to couple my systems with a very large bus. But in each step of my algorithms, I only act on 1 qubit of that bus. Okay? Yeah.
So 2 questions. So which part of the circuit reflect the parameter of temperature?
Yeah, so I will introduce it in the in the next slide. Okay, good. Any other question?
The discard for reset, that's not repeated in between the intermediate steps here, right?
No.
Okay.
Yeah, so this will only appear in the end of each step. Okay.
So the discarding of those measurements makes it a non-Markovian bath?
Yes, yes, right. Okay. And any other question?
Because I'm not measuring it, do I need a clean ancilla or can it be a dirty ancilla?
What do you mean by a dirty ancilla?
A dirty ancilla means that it has some state that I don't know what it's on, but it's not zero. Most of the time when we start quantum computers into zero, a dirty ancilla is just like a thing that you never reset.
Right, so it does not matter. So it can be a dirty ancilla. So we are okay with it. So the reasons I want to emphasize this is a trace out is because also if we do the measurement, we don't have success probability problem. It will always succeed because it's a trace out process. Okay. Any other question? Okay. So now I will give more details about this Hamiltonian simulation part. So basically here, in each step of my algorithms, what we do is mimic our open quantum system dynamics. Okay. Basically here, what we do is we do a time-dependent Hamiltonian simulation. And this time-dependent Hamiltonian simulation contains three different parts. So first, it contains the system Hamiltonians, which corresponding to the Hamiltonian simulation here. And it contains this omega capital Z, which only acts on the bus, which corresponding to this Z rotation here. And the key component that ensures mixing is I also introduce some interaction terms between my system and the bus. Okay? And in this interaction term, I need some coupling operator AS acting on the system part. Okay? So, and this 0, 1 flip and 1, 0 flip act on the bus part. Okay? And intuitively, you should imagine this AS as the coupling operator in my Lindblad dynamics. Using this AS, so I can guarantee that my eigenvectors can be transferred between each other. Okay, and the key thing here is in practice, I will always choose this AS to be local coupling operator. For simplicity, you can basically imagine this AS as local polys, so single qubit local poly. Okay, so this essentially means that although this is a large rectangle, but this part is basically two local gates. Very simple to implement. Okay, and in my algorithm, this the information of temperatures will enter at the initializations of my bus. Basically, I will initialize my single ancilla bus at at the thermal state of my bus Hamiltonian. Okay, that's where I have the information of my temperature. Okay.
Okay, sorry, I'm stuck on something.
Okay.
So the bath initialization happens all the way at the beginning, right?
Yeah.
Not in between steps, only at the beginning.
Yeah.
Okay. So this is, I think, back to the dirty ancilla question as well, which is, okay, so let's say you've initialized and you're using your ancilla to cool your state toward your equilibrium temperature. And so now, like, let's say you've done one of these intermediate steps. Okay. And so you now have a dirty ancilla because the ancilla is partially excited or is excited or something.
Right.
The next step, say there's more to cool.
Okay.
So you engage these 2 qubit gates, trying to couple the systems together to further cool the system that you're trying to cool, but the ancilla is warm.
Okay, I see. Yeah. So this is a very good question. So if you only have if you only use one ancilla qubits, then you need to ensure that after every step you have a clean ancilla.
Sorry.
Yeah.
You said you have a large bus.
Right.
And so every new ancilla you use is clean.
Yeah.
You haven't used it to cool anything yet.
Right.
Okay.
Yeah. So I think it highly depends on how many ancilla qubits you want to use.
Yeah, sure.
So if you can allow a large number of ancilla qubits, then for sure you can have very dirty ancilla qubits. But if you only require one ancilla qubit, then you need it to be very clean, right? So,
sure.
Yeah.
And then finally, when you're done, when you've discarded, now you clean all your ancillas by discarding.
Yeah. So finally, when I'm done, I only look at the system part. I only care about the system part.
Yeah. Okay.
So you decide the size of the finite path based on the number of steps you're going to evolve, right? So,
Oh, yeah, right.
Is there anything pathological about going to zero time, or zero temperature or infinite temperature? Like, so if I want to get to the ground state, I would take the time. I would take it to temperature 0.
Right.
Which feels maybe this exponential of.
Oh, no. So in fact, if you let the temperature go to 0, this corresponding to this beta converge to plus infinity, then if you choose omega to be plus, then this will just be 0 state.
There's a partition function.
Yeah. So yeah.
can you do
Here
that
is
with
our
the
partition
finite
function.
path? Can you do that with the finite path? You're going to the zero temperature.
Oh, right. So I can also do it with a finite path, but since we can do it with a single ancilla qubit, and that's how I present it. Okay.
So how long is the time evolution for each repetition? And also, like, by doing this like a simpler version of implementation, what's the trade-off?
What's the trade-off? Yeah. So I will talk about the trade-off later, and I will also tell you how long we need to do this simulation. Okay. Good. Any other question? Okay, so now I will share more details about this algorithm. So in fact, previously, when I introduced this time-dependent Hamiltonians, I don't tell you what this gamma and ft is. So basically, this parameter gamma and ft controls the coupling strength between my system and the bus. You can imagine that if for gamma is larger, ft is larger, this essentially means that there are strong couplings between my system and the bus. Okay, and in our algorithms, I will choose this ft to be some Gaussian interaction function to make sure that the L1 norm of these functions is a constant. But I do want to emphasize that this Gaussian f is a technical requirement to get a better complexity in our paper. In practice, if you really want a time-independent Hamiltonian, you can also choose this ft to be a constant function. This can also work in practice. Okay. And here, when I choose this to be Gaussian interaction functions, I need to choose this sigma to be a large number, so that my fixed point can be correct. So I will introduce how large this sigma need to be later. Okay, and here in my algorithms, I also have the parameter omega, and in practice, we will also choose this omega randomly. So for examples, you can choose omega uniformly from 0 to 2 times the norm of h, and this distribution is also flexible. Okay, so then in my algorithms, I also need to choose the coupling operator as, and in practice, we will also choose this as randomly. So some specific example is if you want to cool down some spin system, then you can choose as randomly from a single poly set. If you are in the fermionic system, then you can choose as from single creation annihilation operator set. Okay, but the key is all of these as are local operator to make sure that these rectangles are local operator. Okay, good. So now
So this cross operators, they are actually a resolution of identity, but if you do that, will you still have that thing?
What?
The cross operators, if you add them all, it adds to identity, right?
the cross operator, you mean this as here?
Not as the case, the kappas. So you create kappas using the K operator, the cross operators.
So in our algorithm, in fact, we don't have you mean that after I formulated this quantum channel, I write it as a cross operator?
Yeah.
Yeah.
So that should form a resolution of identity, which means if you add up all of them, it should add to identity.
Oh, right. Yeah, that's correct. Okay.
Could you explain what trade-offs the interaction function affords you?
Yeah, so in fact, I prefer to postpone these questions because these questions is related with the third part of this talk. Okay, okay. Yeah, so I will try to answer your questions in the third part of this talk. Okay, good. Good. So now let's talk about the simulations of these algorithms. So as I emphasized before, in each step of my algorithms, I basically do a time-dependent Hamiltonian simulation. And this essentially means you can just pick your favorite Hamiltonian simulation algorithm to do it. And here, what I pick is a second-order chortlerization. For me, this is a very simple algorithm. And the advantage is if I do the second-order chortlerization, then I only need to do the forward Hamiltonian simulation. So there is a no controlled and a backward Hamiltonian simulations. So of course, if you have a better Hamiltonian simulation algorithm, you can also improve the complexity here. Okay, so you just need to pick your favorite Hamiltonian simulation algorithm to do it.
What happens if you use first order trotter?
So then this complexity will become to t to the power 2 over epsilon. Yeah, so that's the only difference. Okay. Any other question? Okay, good. So in fact, this numbers is not the total complexities of my algorithm. So as I mentioned before, here I have an iteration algorithm. So then the total complexities of my algorithm equals to this number times the numbers of iterations. Okay, and this number of iterations is determined by the mixing time of my quantum channel. Basically, the meanings of this mixing time is how many times I need to apply my quantum channel phi to make sure that my quantum state is closer to its fixed point. Okay? So basically now, if I want to quantify the end-to-end complexities of my algorithms, I need to consider the complexity in each step of my algorithms and how many steps I need to run. And usually, in this, in the open quantum system community, bounding the mixing time is the most difficult part. Okay, good. So now I want to provide some theoretical result. Basically, so in our papers and our very recent papers, we can show that for a large class of Hamiltonians, we can have good mixing time. So we can take the thermal state as an example. Basically, if I have a weak interacting systems or 1D local or high temperature local Hamiltonian, then to prepare the thermal state up to epsilon precision, the total Hamiltonian simulation time scales polynomially in beta, polynomially in the number of qubits, and 1 over epsilon. Okay? So in our algorithms, to make sure that I can get epsilon precisions, I need to choose my sigma scales as a 1 over epsilon. And in my algorithms, the simulation time capital T scales as a linearly in sigma. And also, in all of this result, we need to assume that the interactions between my systems and the bus are very weak, meaning that this parameter gamma scales as order epsilon. Okay, so this is a result in our previous papers and our very recent work. Okay. So here I want to briefly introduce the proof ideas for this framework. So essentially, one reason we consider the weak coupling regime is when I choose my gamma to be order epsilon, I can show that my quantum channel can be approximated by a Lindblad dynamics, meaning that although I'm doing a system-bus interaction framework, but because my coupling operators my coupling strength is very weak, the whole dynamics can be approximated by a Lindblad dynamics. Okay? Then after I have these approximations, I can get rid of these high order terms. Then I can show that this Lindblad dynamics contains some jump operator for me to preserve my target state. And also I can use this Lindblad dynamics to quantify the mixing time for my original quantum channel. Okay? Basically, by consider this weak coupling regime, I can guarantee that my quantum state will converge to my target state, and also I have an upper bound for my mixing time. Okay, So, any question here? Good.
Yeah, sorry. It's probably a vocabulary thing, just because I come from a slightly different subfield. But
yeah,
I'm just checking here. When you say weak coupling regime, I think you just mean that the coupling is strong enough that you can toss an excitation over with some kind of a swap via the 2-qubit gate.
Right.
But it's weak enough that you're not actually perturbing the eigenstate of the system that you care about.
No. So in fact, I will still perturb my eigenstate. So otherwise I cannot converge. So the definitions of the weak here is my dynamics can be approximated by a Lindblad dynamics. Yeah.
You said that already. Yeah, it's just that's not a thing I understand, but that's fine. Don't explain it. I'm the only one in the room that needs that.
Sorry, maybe I missed it. Theorem 1, you were saying applies in those special situations?
Yes.
And then what about theorem 2?
Oh,
also?
yes. So in this theorem 2, currently according to our proof technique, we can only do 3 fermions. But I strongly believe for all of these systems, so at least for these first two cases, the theorem 2s are also valid. So we do have some numerical result to support this fact. Okay.
Sorry, what does weak interacting system mean?
Yeah, so the weak interacting system means that you can imagine you have a Hamiltonian capital H, which can be written at H0, which is a separable system, plus some H1, which is a local Hamiltonian. And I need to add a coefficient epsilon here. And this epsilon needs to be smaller than a constant C, where this constant C does not depend on system size, but depend on the locality of my H1. So that's the definitions of weak interaction.
That is, say, when the system interacts with each one of the ancilla qubits, that is independent.
Right.
That's what it means by weak interaction.
Right. Yeah.
That's basically Markovian.
Right. Yeah.
Sorry, are all of these like examples of conditions where this will work, or are all of these necessary conditions for theorem 1, weakly interacting 1D high temperature?
Yeah. So these are sufficiently conditions, but definitely not necessary. So yeah.
But
so
if this works for arbitrary beta, then you're saying that you can do thermal phase transitions, which would be surprising.
yeah. So for all of these weak interaction systems and the 1D local, I think we are fine. Yeah. And this is true for any beta greater than 0.
I see. So for those systems, there are no thermal phase transitions. So there's
Yeah. Right.
What do 1D local and high temp local mean again?
Local means that your Hamiltonians can be written as the summations of Hj, and each Hj are strictly local Hamiltonians, so only act on finite number of qubits.
Okay. And the 1D aspect?
1D aspect means that your Hamiltonians is defined on a 1D lattice.
Okay. Thank you.
Okay.
What does it mean for something to be high temperature local?
High temperature local means that, for examples, if my Hamiltonians is defined on the 2D lattice, then it's very hard for me to show that it has a good mixing time for general beta. But when my temperatures is sufficiently high, I can still show that even in this case, I have a good mixing time.
These are ors, not ants.
You mean yeah, yeah, okay. Okay, sorry, okay, good. And any other question? Okay, good. So now I want to talk about the third part of this talk, which is beyond Lindblad dynamics. I think this is a very interesting observations recently. So basically, according to my previous algorithms, what we know is to guarantee that this algorithm can converge, I need to choose this coupling coefficient gamma to be very small, so that the whole quantum channel can be approximated by a Lindblad dynamics. The advantage of doing this is theoretically simple. Basically, I only need to study this Lindblad dynamics, show that it can fix the ground state, and then I study the mixing time of my Lindblad the bladder dynamics, this can directly give me a mixing time of my quantum channel phi. Okay? But the disadvantage is, since the interactions between my system and the bus is very weak, you can expect that the mixing time of my quantum channels will be bad when I choose my gammas to be very small. So in fact, theoretically, we can show that this mixing time scales as 1 over gamma square. Okay, meaning that if I choose my gammas to be very small, then my tau mix will be very large. Okay, so one very interesting observations in our recent work is we can show the correctness of these algorithms even beyond the Lindblad dynamics regimes. So basically, in my previous result, I require my gamma equals to order epsilon to guarantee the correctness of my algorithm. However, in our recent paper, we can show that even I choose this gamma to be order 1, I can still ensure that these algorithms will converge to the correct state. Okay? So the meaning of this is when I try to study my quantum channel phi, I can also take all of these high order terms into considerations. And I can show that these high order terms are okay in my analysis, meaning that all of these high order terms can still fix the correct target state, meaning the thermal state or the ground state. Okay, so this algorithm can theoretically go beyond the Lindblad dynamics, and we no longer require weak interaction between system and bus. Okay, so one main advantage of this beyond Lindblad dynamics regime is it can reduce the complexities of our algorithms. For examples, here, if we assume that we use the optimal Hamiltonian simulations to simulate this time-dependent Hamiltonian, then the optimal simulation cost scales as capital T times the tau mix, which essentially equals to sigma times the tau mix. Now, if I I choose my gamma to be order epsilon, since the tau mix scales as 1 over gamma square, the total cost scales as sigma square over epsilon square. Okay, but here, if I choose my gamma to be order 1, we can theoretically prove that this can help me to save a 1 over epsilon square factor. Okay, so
the number of ancillas increase in this process? Or?
No, the number of ancillas are still the same. Okay, good. Okay, so basically, yeah. So this is how we get our result, but it's not very important in this talk. Essentially, we can theoretically go beyond the Lindblad dynamics, and by choosing large gamma, we can reduce the computational cost. And conceptually, what we prove is the open quantum system based state preparation algorithm can theoretically go beyond the Lindblad dynamics. So although the Lindblad dynamics is mathematically beautiful, but when we design these algorithms, we don't need to restrict ourselves into the Lindblad dynamics regimes. We can find some way to go beyond it. Okay. Yeah. So here I want to quickly show some numerics to convince you that the theoretical result is correct. So basically, I run a very simple examples, 1D Hubbard models with 4 qubits, and I define gamma equals to alpha times the square root of sigma. This is the notations in our first papers, and you can see that even I chose my gamma equals to 1, my fidelity will still converge from 0 to 1. So here I do want to emphasize that this whole algorithm does not care about the initial state, meaning that even you start from a 0 overlap initial state, you will still converge to the correct ground state. Okay, and here in this graph, we calculate the spatial gap of my quantum channel, and we can show that for different sigma, it has the same spatial gap, meaning the same mixing time, and also the mixing time scales as 1 over alpha square, meaning 1 over gamma square.
Can you restate that it doesn't care about the initial state? And my specific question is, if I start with overlap 1 e to the minus 17, or I started with the overlap 0.999999999, does it take the same amount of time?
Okay, no, yeah, definitely no. So Here, when I say that it does not care about the initial state, the meaning is for arbitrary initial state, we can always guarantee convergence. But of course, if you start from a good initial state, then it will converge much faster.
Like much linearly, exponentially, logarithmically?
Just that?
I think linearly. Yeah.
Can you prove like anything about like the
Yes.
whether the improvement will monotonically increase?
What do you mean by
Like if you were starting from like a state with some overlap,
Okay.
and you run this like Lombardian algorithm, the overlap between the ground state and the intermediate state will like monotonically increase.
I think it's a little harder to prove that this fidelity will monotonically increase. Yeah, so I do think it's a little hard. What we can do is we can only guarantee how fast it increases. But you might see some like zigzag. Yeah, so it's very possible.
I have a question that you can just tell me you don't want to answer.
Okay, it's okay.
You want to get on with your talk, but looking at the fidelity there as the measure on the y-axis, I'm imagining like taking a big chunk of Hubbard model and putting it in the fridge. And what I really would care about is not that the overall state has good fidelity with the thermal state or the ground state,
Okay.
but that like, some local reduced density matrices are correct.
Okay.
That's a weaker requirement.
Yes.
And I wonder if it's possible to take advantage of that weaker requirement in the context of these algorithms.
Yeah. So I think sure, this is definitely a very interesting question. But as you can see in my talk, this is a very new area. So we just developed for 2 years, and I do think at least from my point of view, one future directions will be try to further simplify these algorithms and to accommodate this kind of question. Yeah.
Okay.
But I would say I think up to now people only consider the case where we require the whole state converge.
Okay.
Mm-hmm. Yeah.
For your numerical simulations here, what are you using for your A operators?
So here I think for these simulations I sample my A from single creation and annihilation operators.
So you're not conserving particle number in this case?
Yeah. No. Not conserving particle number. Yeah.
So what you're converging to some ground state of how many particles?
How many? So here I have a four. So in fact, I do think this corresponding to like two different sites. So only 2 particles. Yeah. So
Does your thermal state have a fixed particle number?
does my thermal state has a fixed particle?
Is it canonical or grand canonical?
No. Yeah. No. Okay.
So, since you've said you can go beyond Lindblad
Yes.
and you can use larger gammas, it's obviously you're doing it. Is there a downside to going to larger gammas? Like, do
Yeah.
you sacrifice anything? Does it cost you more? Anything like that?
Right. So I will mention this in the end of my talk.
Great.
So it looks like on for the first 3 steps, the fidelity is constant,
Okay. Yeah.
and then it jumps up. Can you help me interpret that?
Yeah. So the reasons it sometimes happen because, for example, I will choose my Compton operators AS randomly, and there is a chance that I choose some AS that does not help, meaning that my AS cannot transfer one eigenvector to another eigenvector, and that's the reasons why I might get stuck sometimes.
There are ways to guarantee fixed points in a Lindbladian dynamics. How do you do that here?
Oh yeah. So currently, I think to my best knowledge, this is still open problems in our framework. Yeah.
So I was wondering, for the fidelity against step graph, if I run this for a gapless model, what would the graph look like? Would it go to a plateau below 1, or would it just like stay flat all the while? Or like?
Right. So very nice question. So if you run it for a gapless model, then then so since in our algorithm, the only information about the Hamiltonians I can get is the Hamiltonian simulation. Then if you have a gapless model, then it's very hard for me to distinguish the ground state and the first excited state. Yeah, so it's true that then this fidelity will meet some plateau. But if you consider the fidelity of both ground state and the first excited state, and you sum them up, it will still converge to 1. Yeah. Mm-hmm.
3 minutes.
3 minutes? Okay. Yeah. Any more questions? Okay. So yeah. So since there are only 3 minutes, I think I will quickly go through the remaining part. So in fact, I think another interesting observation from our paper is in our paper theoretically we can only prove the correctness of my algorithm once the gammas equals to order 1. But in fact, according to our numerics, this algorithm will still succeed even I chose very large gamma. So even I chose my gamma scales as order sigma, this algorithm can still converge to the correct state. Okay, and if I bring gamma to be larger, then this mix will even be faster. Okay, so and another thing I want to comment is for all of this open quantum system dynamics problems, so we don't worry too much about a phase transition. So here I consider the ANNI model, and we can show that if you only run the adiabatic dynamics on this ANNI model, then you don't converge to the correct ground state. Okay. However, if you run this open quantum system dynamics, it will still converge to the ground state. You can show that this energy will still converge to the ground state energy. Okay, so since I only have 3 minutes, I think I will skip this part. So this part is basically tell you that if I have some open quantum system dynamic mix algorithms, then I have a way to prepare bunch of low energy eigenstate. Then there is some algorithms for me to use this low energy eigenstate to produce some physical information of my Hamiltonian capital H. Yeah, but I will skip this part and directly go to the future direction. So one interesting future direction is I do want to see some early fault-tolerant quantum computer implementations of my algorithm. So as I emphasized many times in my algorithms, so in each step, I only need to do the Hamiltonian simulations plus trace out. The meanings of this is the simulations of my algorithms, its difficulties is almost the same as the Hamiltonian simulation. So in fact, I don't see any difficulty to implement these algorithms on the early fault-tolerant quantum computer. And I also believe this algorithm framework can be noise robust because our algorithms depend on some contraction map. And even you have some noise, this noise will be contracted in the thermalizations. And I will also be interested to see the resource estimations of my algorithms. Okay, so here I also want to comment on the choice of sigma. So in our algorithms, I need to choose sigma to be 1 over epsilon. The reason is I want to go beyond the Lindblad dynamics regimes, meaning that I want to choose gamma to be order 1. Okay. However, if I choose my gammas to be very small, we have some ongoing work showing that I can choose my sigma to be order 1. So there is some kind of a trade-off, meaning that if I can remain on the Lindblad dynamics regimes, I can choose my sigma to be order 1. This is definitely okay. Okay, and another beauties of this algorithm is this is very flexible. So in fact, in this algorithms, there are a lot of things we can tune. So we can tune the choice of the parameters. We can tune the choice of coupling operator AS. This essentially means that I think this algorithm can be combined with a lot of different state preparation algorithms. So essentially, we can borrow their idea to design the choice of these parameters. Okay, And this algorithm can also be combined with other quantum computing algorithms, such as quantum phase estimations, to estimate interesting physical quantities. Okay, so that's all my talk. Thank you.
We have time for one question.